Okay, so we've been talking about the electromagnetic model, the scalar model, back to the electromagnetic model, and last time we kind of did a comparison between the two. We said for the scalar model, we have a complex representation of a monochromatic wave that is just a complex amplitude times e to the j omega t. And then for the electromagnetic model, we have an electric field complex representation that is a complex amplitude vector times e to the j omega t. So monochromatic, the two different models. And you see, other than differences in symbols, this is a scalar complex amplitude. That's a vector complex amplitude. This is a solution of the scalar, or rather the electromagnetic wave equation. This is a solution of the scalar wave equation. This piece is a solution of the complex, or rather the Helmholtz equation. Each Cartesian component is a solution of that. And this is a solution of the Helmholtz equation. Okay, and we talked about plane waves in both cases. We found that for the scalar model, the irradiance is magnitude squared of the complex amplitude, so this would be irradiance as a function of position. And for the electromagnetic model, it was much more involved to get there, but we finally found that the irradiance is 1 over 2 times the impedance of the medium that we're propagating in times magnitude squared of this constant complex vector for a plane wave. So in other words, plane wave, we have that in the scalar model, this is a constant, a complex constant times e to the j minus j k dot r. And in the electromagnetic model, the electric field complex amplitude is equal to some constant complex vector e to the minus j k dot r. And so the irradiance of a plane wave then is this, and I believe you show that in the homework. Okay, so we can calculate irradiances in either model. That's good. And whenever we do monochromatic stuff, we know what to do. Plane waves, we know what the representation is, and we'll talk a lot more about that later. What we want to do today is take a step back and look at a different property of optical fields, and that property we call coherence. So we want to understand coherence, and in particular, we're going to talk about two idealizations. The first idealization is temporal coherence, and the second is spatial coherence. So with temporal coherence and spatial coherence, what I want to do is give you just sort of a visual conception of what it means with no math, and then I want to dive into the math. And the math only insofar that we understand basically what's going on and can use the relevant things. So we don't have to go down that rabbit hole too far. But first of all, let's just have kind of a notional idea of what temporal coherence means and then spatial coherence. So let's say that I have some real optical field, and let's say I'm looking at a specific position in space, r0. And let's plot that field as a function of time. And if it's monochromatic, then what it will look like is just sinusoidal, as usual. So this is the monochromatic case. On the other hand, if I have a polychromatic wave, it's not going to look nice and sinusoidal. it'll be something else. You know, it'll do something like this. Whatever. Okay.
Does it have to, it doesn't necessarily have to be a repeating pattern, it can be,
Yeah, it won't be a repeating pattern.
so it won't repeat that ever.
Yeah, well, it can repeat, but it doesn't have to repeat.
Okay, so, okay.
Yeah, because remember, our picture of a polychromatic wave is a set of monochromatic waves. If we have a finite set, and we add them all together with random phases, then we will get a pattern that repeats. If, on the other hand, we have a continuous set with randomly varying phases, then it doesn't necessarily repeat. Yeah. Okay, yeah, very good question. Okay, so now I want us to consider the following expression. And that expression is the field at that point, R0 we're considering, at some time t. And let's just say we subtract off of it the field at the same point at some time t plus tau. So what does that mean? Well, here we have, for the monochromatic case, u of R0 of t, so that is this term. Here, all we've done is taken that, made a copy, and shifted it by tau. And actually, we've shifted it backwards by tau, because we have plus. Okay, so if we look at the difference between the two, we're just looking at the difference between the wave itself and a shifted version of it. Now, if we shift it just slightly, just a tiny amount, then they're not going to be very different, right? And in fact, we could think about the correlation between those two fields, the original and the shifted one. And if we shift them just a little bit, they're still really correlated. If we shift it more, it turns out there's still a fixed functional relationship between them in this case, because this is sinusoidal. In this case, though, if I shift it just a little bit, yeah, it's still correlated. But if I start shifting it more and more and more, there's no fixed functional relationship between the two anymore. It becomes random. So we would call, then, this situation coherent, and this situation incoherent. Specifically, temporally coherent, temporally incoherent. So the notion of coherence, temporal coherence, is take a wave, a beam, an optical field, make a copy, shift it in time, look at the correlation. If there's no correlation, there's no fixed functional relationship, we say that we have temporally incoherent light. Now, why would we care? Well, interference is exactly that situation. Two-beam interference is, we have a beam, we make a copy, we do different things to them, we bring them back together, they interfere. And so, if we want them to interfere, it turns out they must be coherent. And then we'll get the expressions we'll develop later in the class for coherence. If they're not coherent, meaning they're incoherent, when we bring them back to interfere, they're not going to interfere. There will be no interference terms. Yeah?
Here you have monochromatic and polychromatic. Not all polychromatic waves are incoherent, right?
We're going to figure that one out.
Okay.
Yes, you're poking in a very fruitful area.
Okay.
Yes.
So also, the coherence of the monochromatic wave, it's only for the case that that tau is small, right? Or not small, but small.
So it depends on how, so forgetting this label of monochromatic, we just see something that looks pretty sinusoidal. And then we, so here's basically a period. And if we go over, say, 3, 4, 5 periods, it still looks like it's really sinusoidal. What if we went 1,000 periods away? is it still sinusoidal with this period and has, everywhere in between has exactly the relationship we would expect for a sinusoidal wave? Then it would be temporally coherent over that entire range. But, yeah, but we'll see how it goes. Yeah, yeah, Dave.
So is there another constraint on this, maybe according to what you were saying? Because I don't see, if that was a signal, you can decompose it into its frequency components.
Mhm.
Wouldn't there still be a functional relationship then to time shifted of a decomposed signal like that?
Of the individual components, yes.
Of the individual.
But summing them all together, no.
Ah, okay.
That's the key thing, when they're all summed together. And I could take the two beams and put them through very narrowband filters. So I'm just pulling out one frequency component on both and bring them back together, and now they look good. I mean, yeah. Fair?
Yeah, I want to ask, mathematically to check they are coherent or not, can we use cross covariance or is different?
I'm going to leave that until we do the math in just a minute. But it's a good question, yeah. Okay, so this is a kind of a simplified picture of what temporal coherence is all about. So I hope you kind of have an intuitive sense at this point. Now, let's do spatial coherence. And again, we're just going to develop a mental picture of what this could mean. So, if now I plot, let's say this is the z-axis, this is the x-axis, and I plot as a position of space, but at some fixed time t naught. So I've frozen it in time. I'm just taking a snapshot, and I plot the wavefront, say. So let's say the wavefronts look like this. Okay. So if I put myself, say, right here at position P, and look this way to position P prime, then I could play the same game. I could look at the field at position P time T naught and the field at position P prime time T naught, and I can ask, is there a fixed functional relationship between the two? Are they correlated? And in this case, you say, well, yeah, obviously, they are. But what if I took, and again, this is just a mental exercise. What if, if these are wavefronts, then we saw that the propagation direction is perpendicular to the wavefront. So clearly it's propagating in this direction, right? What if I could take the beam and slice it up like this, and take this slice and just give it a random phase shift. So now I'm over like this. And this slice, I give it a random phase shift. So now it's back over here or something. And this one, I give it another random phase shift. So what if I took my beam and took a whole bunch of slices and just randomly shifted them? Then, if this is very far away from that, it's no longer going to be correlated with that. And that's basically what spatial coherence is all about.
So it's like part of the wavefront moves faster than another part?
It's kind of like you have a piece of glass and you have a one-dimensional set of stripes such that the glass has a different thickness for each stripe.
Okay.
Then basically, as you propagate through it, you're phase shifting
Got it.
each little piece of the beam. So that's one way you could do it.
Okay.
Or you could have a two-dimensional set. So you've got these little pixels of different heights. So now you've randomized in 2 dimensions. Then, if you take your original set of wavefronts, make a copy. Well, no, let's not do that. If you take your shifted wavefronts like this and let P prime be pretty close to this one, then you're still gonna have spatial coherence. They're still gonna be correlated. There's gonna be a functional relationship between them. But if I go over here, now there's not as good a relationship. If I go, say, 50 of these over, I mean, there's just no relationship. It's just random. Yeah.
And so spatial coherence has to do with the same wavefront, right? It's not like comparing one point on the wavefront to another.
In essence, yes, for the moment, with this simple sort of intuitive model. You could also say, well, gee, what if I don't go orthogonal to the wavefront? What if I go over here, and consider P double prime? Well, now I have a component parallel to the wavefront and a component orthogonal to the wavefront to get there. Orthogonal to the wavefront is the same thing as time. And so clearly, thinking about temporal coherence as a completely separate thing from spatial coherence is an idealization. In reality, it's all part of the same thing. But it is helpful to conceptually think about them separately. In fact, it turns out to be extremely helpful. Okay, so that's our intuitive picture of coherence. Now let's develop the math a bit. And in the end, by the end of today, what we want to do is take this intuitive picture, take all the math, and come up with 2 rules of thumb. Rule of thumb being a very simple, in fact trivial, algebraic equation. So we'll have 2 trivial algebraic equations that will encapsulate temporal coherence and spatial coherence. And with this mental model and those 2 little equations, we can do pretty much anything involving coherence. It's awesome. So that's what we want to develop today. So let's first of all develop our quantitative description now that we've done a qualitative description. And whenever we start out on one of these endeavors in optics, the first thing we always have to specify is what model are we going to use. So we have 2 choices, scalar model, electromagnetic model. Which one would you like to use? Why?
Because I need that.
Yeah, it's all 4 dimensional, yeah.
Yeah, all the spatial dimensions. Okay, so let me introduce you to a different way of thinking. Scalar model is simpler than the electromagnetic model. So we're trying to learn something new, always choose a simpler model. Because once you get it in the simpler model, usually it's not very difficult to generalize to the more general model. As opposed to diving into the general model and getting lost in all of the details of it and not extracting, the main ideas. Because the key is always, what are the main ideas? And once you have the main ideas straight, then you can always look at the complexities. Okay, so our first choice then that we have to make is scalar model. So we'll assume scalar model. And then we need to make an assumption about the kind of optical wave we're going to look at. And we're just going to pretty much make no assumptions and say general polychromatic light. And for general polychromatic light, then we can't write a complex representation like this, right? Because this is for monochromatic. So all we can say is, the complex representation is that. It has some space dependence, it has some time dependence. Or alternatively, we could look at the real optical field, but we can't really say anything more than it has some spatial dependence and some time dependence. So that's about all we get. Okay, now what we want to do is define something that we'll call the mutual coherence. And the mutual coherence, we'll give it the symbol capital gamma sub 1, 2 of tau, and we'll write it as the product of the complex representation of the field at position R1 time t and the complex conjugate of the field at position R2 at time t plus tau. And then we want to average that thing. And in general, this average is an ensemble average. What does ensemble average mean? Basically that U is a random function, and we're averaging over many realizations of the random function. Now, if the light is stationary, which we will define shortly, if it's stationary, then the average is a time average. And that's not a very restrictive assumption, because generally we're going to talk about stationary light. Okay, so that's our mutual coherence. And basically what is it? Well, it's the average correlation of the field at position R1 with the field at position R2 shifted in time by tau. Okay, so keep that in mind, an average correlation. And now let me write down. Yeah.
What do you mean by stationary again? Is that like the light source?
I haven't defined it.
Okay.
Yeah, we're going to define it shortly.
Okay.
Basically, it just means constant irradiance.
Okay.
So, but yeah, we'll get there in a moment. Okay, so recall what the expression for irradiance is for a polychromatic beam. You remember?
What? So E naught over 2 eta.
Enoch, what model is that?
Oh, sorry. Yeah, sorry. That's EM model.
Yes.
A squared, I guess. Yeah. Absolute value of A squared.
Okay, and A square, or A, what assumptions went into coming up with that symbol? Monochromatic plane wave. And here, you've got general polychromatic light.
So that is two
Yeah,
times one.
so I'm glad you mentioned that, because this points up the whole notion of, yeah, what are our assumptions, what's our terminology, and notation, so that we get it all straight in our mind. So that's great.
Absolutely.
Yeah.
2 times integral u sub mu e to the 2 pi.
So that is the definition for the complex representation of general polychromatic light.
So it's gonna be the magnitude of that squared, right?
Magnitude of that squared, and let me write it a little differently. So U of RT, mu complex conjugate of RT. Right, that's magnitude squared?
Yeah.
Yeah.
And then this is instantaneous. This is, I mean, we don't care about the instantaneous irradiance. We always care about the time average irradiance. So we take the time average. Yeah. So we compare this to that, and we say, yeah, that looks really similar. And in fact, if we subscript the R with a 1, so we're just talking about a particular position, R1, which could be any position. Notice this is just gamma 1, 1 of tau. So in some sense, this mutual coherence function is a generalization of irradiance. We're just no longer looking at the same position or the same time. We're generalizing. Yeah.
Is that a tau equals 0 for the?
Oh, yes. Thank you very much. You're right. Thank you. Yeah. Perfect. Okay, so this mutual coherence is a generalization of irradiance. Great. And in general, this mutual coherence is going to depend upon which 2 positions I pick and what temporal separation I pick and just the nature of the light. Okay, now, what we want to do is define a normalized version of this. So let's define little gamma 1, 2 of tau as capital gamma 1, 2 of tau divided by the square root of gamma 1, 1 of 0 and gamma 2, 2 of 0. And then you'll recognize the denominator as just the square root of I1, I2, where I1 is the irradiance of position R1, and I2 is the irradiance of position R2.
What did you define this as again? Little gamma?
Little gamma is a normalized version of the mutual coherence, and we give it a name. We call it the complex degree of coherence. So that's its name. Okay, and so it's just a normalized version of the mutual coherence. Okay, now another definition. If we take the complex degree of coherence and just take its absolute magnitude, we call that the coherence. So when we say coherence, there's actually a mathematical expression that we mean when we say coherence. And the beautiful thing is that expression right there is easily measurable in the lab. So measuring the coherence is not that big of a deal. And we'll talk about how later. And so if gamma 1, 2 of tau is 1, we say that the light is coherent. If gamma 1, 2 of tau, magnitude thereof, is 0, we say that the light is incoherent. And then everything in between, we say that the light is partially coherent. Okay, so now we have a specific definition for each of those terms, coherent, incoherent, and partially coherent, all in terms of that coherence function. Okay, now we can give meaning to the term temporal coherence. When we say temporal coherence, what we mean is the coherence here, where we're evaluating it at the same position. So it's gamma 1, 1 of tau. So that means we just have R1 and R1 here.
So does that mean that we're looking at it at a different time?
Yep. Same position, different times, you know. And tau is basically a time shift, which is the same thing as saying, take your field, make a copy, shift it in time by tau, compare it.
So when you said over here that gamma 1, 1 is tau is equal to 0, that's just saying that there's no shift?
Yeah, so there's no shift. So it's same position, no shift.
So the subscript is the position.
Yes. Mm-hmm. Yeah.
So when it's 1, 2, that's two different positions.
Yes.
Okay.
Exactly. And so that means then that spatial coherence is the coherence gamma 1, 2 of 0. So two different positions but the same time. In other words, we take a snapshot and then we look at two different
Do we
positions.
just arbitrarily choose 0 then? Could be any time, right? Or
Oh, it's tau is 0.
okay.
So the time
Oh, okay,
shift
gotcha.
is 0. Yeah.
Gotcha.
Yeah, good question. Okay, so when we talk about coherence, that's it. That's what we mean by all those terms.
Definitely, can you explain the complex degree of coherence?
What's that?
The complexity coherence, the small gamma.
Yes. Well, no, because this is averaging over that time. So it's a time average for stationary light, meaning constant irradiance. And here, this time dependence is not really that time dependence. I should probably remove it. It's the slowly varying irradiance. This is averaging over the really fast variations of the field. And then if it's stationary, then this by definition is constant. Yeah.
And then with the ensemble average, are you doing the ensemble average because we're dealing with polychromatic light and we're trying to treat everything as a monochromatic wave, and you're just averaging each one of those?
So it's this or it's that. And if the light's stationary, this is a time average.
Okay.
Stationary means constant irradiance.
Okay.
If it's not constant irradiance, then we do an ensemble average, which means this random function, we just take many realizations of it and average them together.
Okay, okay.
Yeah. Which in practice, you can't really do. Yeah. Fred?
Excuse me, can we say irradiance is like autocorrelation and then evaluated at 0?
Yes, exactly. That's exactly right. Perfect. Yeah.
So, I guess I'm not understanding this arrow bracket notation. Like what type of function that means, because I'm used to that being in your product.
Right. So erase that from your memory as far as this class is concerned.
Yeah, so what?
So it's a time average. So it's a, it's an integral something over time. But the integral extends, so if it's periodic, the integral is over one period.
Right.
But for non-periodic, what is the time interval we're integrating over? Something short, but not too short.
Okay.
That's about all we can say at this point. Yeah.
Fair enough.
But if the light is stationary, meaning that the irradiance is constant, then this integral could be from 0 to infinity, because the irradiance never changes, so it doesn't matter. So, in other words, if we were to plot the irradiance of this thing, then so plotting irradiance here, it would be that. It's just a constant irradiance. If we plot the irradiance of this thing, if it's stationary, then again, it's just that. But if it's non-stationary, then it'll be something that varies in time slowly in comparison to these rapid variations of the field itself. Yeah.
When you say stationary, what do you mean by that?
Constant irradiance. So stationary means that I is constant over time. In other words, you have a laser, you turn it on, it warms up. After it's warmed up, it just puts out the same amount of power all the time, never changes. If, on the other hand, you took the power knob and you're just kind of twisting it, so now the power is going up and down, now it's not stationary anymore.
Yeah, but you don't understand the switch.
Yeah. If it's monochromatic like the laser. Yeah, if you have a white light source, like you take an incandescent bulb and you change the voltage across it, well, it's a polychromatic source. And if you just keep the same voltage across it, the irradiance is the same. Even though, these fluctuations are just kind of random. But they're really fast, and we're time averaging over those fast fluctuations, and that gives us just a constant irradiance. On the other hand, if we take the voltage knob and we run it up and down, well, now the irradiance is a constant, it's varying according to how we're turning the knob. But we can still do a really fast time average to average out the field fluctuations of themselves. And then we're left with that slowly varying irradiance. Okay, so any other questions? All right. So what do we do with this? So let us now think about, go back to temporal coherence. Now that we've developed these various functions, then, and we're assuming stationary light, so constant irradiance. And if I take the complex representation of the field at position R1 as a function of time, and I take the real part of it, so that's the real field then, and I look at that as a function of time, then it's polychromatic, so it's just, you know, something, whatever it is. And then if we consider the temporal coherence, then we can say a couple of things. First of all, this is polychromatic, so it's going to be, well, let me back up. Let's do it this way. Let's consider gamma 1,1 of 0. So let's consider the coherence, the temporal coherence, when tau is 0. What is that?
That'd be like 100%. It's the same time, same position.
One.
And so this is the normalized mutual coherence. So at 0, the value of this is going to be what? 1. Okay. And then if we consider gamma 1,1 of tau, and say tau is really big. How big? I don't know, just really big. Then what value is this going to have? 0. Okay. So from those two facts, we can extract a really interesting conclusion. And that is, if I plot the temporal coherence as a function of tau, I have some data points. I've got this point right here, that's just 1. And when I go way far over here, it's 0. And when I go way far over here, it's 0. So I can guess what the curve looks like. And it's going to look something like that, right? Right? It has to. It'll have some shape, whether it's Gaussian-like or Lorentzian-like or whatever, but who cares? It's going to have that basic shape. And moreover, if I look right here, that characterizes the width of that shape. And we give that width a name. We call it tau sub c, which is the coherence time. So in other words, if we take this light, this field, make a copy of it, and shift it by tau less than about tau c,
We're still coherent.
yeah, we're still pretty coherent. If we take it and shift it by, say, 5 times tau c, we're pretty much incoherent.
So is tau c just some arbitrary threshold that we're calling coherent enough?
Yes, so this could be the full width half max, it could be the 1 over e points, it could be the half width half max, whatever. I don't really care. What I'm focused on is just that we can define some method of saying what the width is. Whatever method we choose, and we can use that width as a scale with which to judge tau and how coherent I'm going to be for a given tau. If I'm significantly less than tau c, I'm going to be pretty coherent. If I'm significantly more, I'm going to be pretty incoherent. So it just gives a single number, that kind of a threshold, even though it is a continuum. Okay, so for a laser, which we typically think of as being quite coherent, then tau c is long, meaning a few picoseconds to a few nanoseconds. For white light, which we typically think of as being incoherent, tau is short, a few femtoseconds. Okay. Now, it turns out that coherence time, usually when you're looking at a source, the coherence time itself is not specified. Like if you buy a laser and you look at the specs, you usually won't see a spec called coherence time. Instead, you'll see a spec called coherence length. So what is that? So we can take the coherence time and convert it to an equivalent length. And that coherence length is just the velocity of propagation of the light times the coherence time. And the velocity of propagation of the light is just speed of light in vacuum divided by refractive index, and then multiplied by the coherence time. And so, if you see a coherence time, usually it's specified in air or in vacuum, in which case n is 1. So it's easy to get the coherence time. Just take the coherence length divided by speed of light in vacuum.
And so if you product coherence length, it's usually specified just in a vacuum or?
Yes. But if you're propagating in, say, glass, well, the coherence length is going to be less by a factor of n, which is 1.5 for glass. For silicon, if you're propagating in silicon, then refractive index is about 3.4. So your coherence length is shorter by a factor of 3.4 as compared to in air. Okay, so now we get to the heart of the matter, which goes back to something Farah said. And that is that this, this complex degree of coherence evaluated at position R1, so gamma 1,1 of tau, that is the autocorrelation function of the optical field. So when you pick it apart and look at the mathematical expression, you recognize it as that. Now, is it important for you in this class to recognize it? No. I'm just telling you kind of the steps here to get to a rule of thumb. And you don't have to have a thorough knowledge of the details of those steps. So once we have an autocorrelation function, then we can go back to the Wiener-Khinchan theorem, or relation. And it basically says that the power spectrum and the autocorrelation of a field that these things are a Fourier transform pair. So if we take an autocorrelation function, Fourier transform it, then we have the power spectrum. If we take the power spectrum and Fourier transform it, we have the autocorrelation function for any field. And so, of course, it's true for an optical field in the scalar model. Okay, and now here's where the beauty comes. Because of that relationship, the width of the autocorrelation function here, the width is tau c, right? And so that autocorrelation function, we're plotting it here, the magnitude of the autocorrelation function. The power spectrum, we could plot it over here as a function of frequency, nu, f sub nu. And let's say our power spectrum looks like this, it's pretty narrow. And so this is the width, delta nu, of our power spectrum. Well, because that and that are a Fourier transform pair, there must be an inverse relationship between their widths. So the coherence time goes as 1 over the spectral width. And that is an absolutely beautiful thing that saves us so much work when we're just thinking about temporal coherence. Yeah?
So are these just proportionate or are they equal?
They aren't exactly equal. Well, so it depends on the exact shapes of these things.
Oh, okay.
But for rule of thumb purposes, just set them equal. You know, maybe for a particular spectrum, it's the coherence time is 0.8 times 1 over delta nu. Yeah, whatever. It's within 20%. Okay, so if we have a very narrow spectrum, that implies that when we look at the temporal coherence, it's going to be it. So narrow spectrum, large coherence, large temporal coherence, meaning long coherence length. On the other hand, if our power spectrum is broad, meaning it's quite polychromatic, then our temporal coherence is going to be narrow. And therefore, coherence time is narrow, and therefore our coherence length is short. So, this is really nice because if we want to know about the temporal coherence of a source, it's trivial to all of us now. Just look at the spectral bandwidth of it. Is it narrow band? Well, then it's pretty coherent. Is it broadband? Well, it's not going to be very temporally coherent. End of story. Okay, so any questions? All right.
So assuming that the power spectrum is just a delta function, would that say that it's really coherent?
Yes, that's exactly right. And of course, when we talk about monochromatic light, then we're talking about just a single frequency. So this is essentially 0. So that's infinite. And therefore, for a plane wave, which is a type of monochromatic light, it doesn't matter what time shift we're looking at, whether it's a nanosecond, a millisecond, 1 second, or 10 years. It's still coherent. Which, of course, means that a monochromatic wave is really an idealization. You never have it in practice. You can get close, arbitrarily close, but as we'll see, that always means you're throwing away power. Yeah.
Is that's the magnitude of gamma is the autocorrelation, or no magnitude?
No magnitude. which means that when we take the Fourier transform, there will be a real part and there will be an imaginary part. But here, we're just looking at the magnitude. Okay, so that is, in a nutshell, temporal coherence. It's awesome. It's so simple. Now, let's do the same for spatial coherence. And again, we're going to find it's so simple. So, spatial coherence. Let's say that I have some set of sources here that are incoherent point sources. Which just means that every source here is emitting with a different random phase compared to every other. So, and these could be monochromatic sources. But I'm going to leave that unspecified for now. And so, let's draw some coordinate axes in here. So let's say we have some source that is a collection of spatially distributed incoherent point sources. Then we go some distance away, some distance r, to this point over here. And then we ask ourselves, over what size of a patch will the light from this look spatially coherent? Meaning that if I take the field here and compare it to the field over there, they're really correlated. And so we can, let's say we talk about the width of this as rho sub c. So that's the correlation length. Alternatively, we could call this a sub c the correlation area. Whatever. Yeah.
Are you saying, like, would those 2 points over there match kind of 2 point sources over here?
Nope.
No.
So basically, a point source that's radiating everywhere, right?
Yeah.
So over here, you know, light from that point source follows that particular ray. Light from this other point source follows that ray, etc. And so at every point here, we're collecting light from every one of those. And we're asking over what area, however small or large, do we have spatial coherence, meaning that there's good correlation between the light at the different points here. And we're not going to go through the details of it.
What did you call rho sub c again?
Pardon?
What did you call rho sub c again?
So this is the correlation length, and this is the correlation area. Or, sorry, coherence length. No, not coherence length. Let's call it coherence width. Okay, so, and here I'm just going to skip a whole bunch of steps. The coherence width goes as the following. Let's say, looking from this on-axis point, the source subtends an angle of, call it theta sub s for the source angle. So that's the angular extent of the source as seen by an observer right here. And this is a distance r away. So, and these things are emitting at wavelength lambda. Then basically the coherence width goes as wavelength divided by the angular size of the source. And so the coherence area is essentially the coherence width squared, which is about lambda squared over theta s squared. And that's essentially lambda squared over d omega. In other words, the differential solid angle subtended by the source as observed from the observation point. So let's call it S. So the solid angle subtended by the source is the and now let's call this area DAS, that's the source area, is DAS divided by R squared. So that's the solid angle subtended by the source from the observation point. Okay, so let's say that this source was the sun, and over here, this is us on the surface of the Earth. Then in that case, this angular size of the source is about half a degree. So half a degree. And that means that the coherence width is going to be wavelength divided by half a degree in radians. And so if we convert half a degree in radians, that's about 8.7 milliradians. So what we end up with is, let's just do this, 1 over 8.7 times 10 to the 3 is about 115 wavelengths. So, light from the sun, as observed here by us, if we look at a patch that's 115 wavelengths wide, that's about the size of the region over which we have spatial coherence of light from the sun. Yeah, which is small. So let's say that our wavelength is half a micron, so we're in the blue-green portion of the spectrum. So the coherence width is roughly 58 microns. So what does this mean? Let's say that we had a piece of aluminum foil, and we punched 2 tiny little holes in that aluminum foil. How small? Just small. And let's say that the separation between those 2 holes is, I don't know, A. So if A is significantly less than 58 microns, then I have really good spatial coherence. But if A is significantly bigger than 58 microns, then I'm spatially incoherent. Okay? So, when we want to figure out spatial coherence, it turns out it's really simple. It's just that. In one dimension. Or you could do this and take the square root to go from an area to a... Yeah.
I kind of have questions about some of the assumptions here. Is R considered the far field?
Yeah, it's far away.
Because the sun, yeah.
Meaning it's many wavelengths.
And then in order for the theta, what you call that, subtended?
Yeah.
Theta S squared to be d to radians, we're assuming coordinate system where it's very near the zero. There.
Yes, yes.
Okay.
Yeah, so this is only true for quite small angles. Yeah. And then it's it's really good, a really good approximation. But if the angle is 45 degrees, no, that's not any good. Then just go to, well, we won't even talk about it because we don't care. But yeah, so yeah, Wes.
So can we just treat each wavelength in the sun individually? Like here we just pick green light or something, but the sun has lots of colors.
It has lots of colors. And so does having lots of colors to first order affect spatial coherence?
Just your distance, right?
Just the angle subtended by the source. That's all that really affects spatial coherence. On the other hand, if we just look at the sun, well, don't look at it, but if we just take the light from the sun, and we ask, well, what's the degree of temporal coherence? And we'll say, wow, gee, I mean, this is huge, so that's gonna be really small. In fact, let's do the following little exercise. Let's consider some different sources. And then let's comment on the source. And then we'll comment on degree of temporal coherence and spatial coherence. Okay, so let's say that we are talking about a star in the night sky. So what would be the degree of temporal coherence? Would it have a high degree of temporal coherence or a low degree of temporal coherence? To answer that question, what's the one thing we have to know? Spectral width. Light from a star, is it broadband or is it narrowband? Broad. So temporal coherence would be high or low? Low. Now what about spatial coherence? Really high, because the angle subtended by the star is so small. So this would have a very high degree of spatial coherence. So if you were designing an astronomical telescope with an aperture of, say, 1 meter, would the light coming into that entire aperture be spatially coherent? Heck yeah. Yeah. So it's beautiful when you're doing optical design for that kind of an optical system, you know you have spatial coherence. Okay. Now, what about, let's say I had a laser, whatever kind. The degree of temporal coherence? High, because it's narrow band. And the degree of spatial coherence? Low.
Just depends.
Yeah,
If you put it through a small aperture, can you get it really high?
So it turns out the laser is a special case. And the laser will have a very high degree of spatial coherence. And the reason is just how the light is generated. And so you just get a lot of coherence. You end up with a Gaussian beam, and the Gaussian beam is temporally coherent. So, yeah. So you get a high degree of coherence on both counts. Yeah, Jason?
So the laser doesn't, for spatial coherence, it doesn't really obey these equations that we derive.
Yeah, you don't analyze
assumption
it this
doesn't
way
apply.
because it violates the assumptions.
Yeah.
You know, we're not.
You're not a collection of point
Yep.
sources.
Yeah, exactly. Yeah, we're not super far away and blah, blah, blah. So, but yeah, the key one is we're not a collection of incoherent point sources. Because the light, I mean, by definition, a laser, in terms of how it works, all the light is emitted in phase throughout the cross-section of the laser. So,
It's always coherent.
yeah, it's always coherent. Okay, so what if I had an incandescent light bulb? What would be the degree of temporal coherence? Low. Because?
Broad spectrum.
Yeah, it's white light. It's really broad. Now, what about the degree of spatial coherence?
Depends how far away it is.
Totally depends on how far away it is. So if you're close to it, you know, you're staring at it right here, then it's going to have a low degree of spatial coherence. But if you're out hiking in the woods and you get up on top of a mountain and you see this lone farmhouse in the valley below and it happens to have its porch light on, and you're a couple miles distant, then what? Then it has high. So you can always generate a lot of spatial coherence by just going far away from the source.
Could you also do it by using a small aperture?
Yeah. Mm-hmm. Yeah. stick a small aperture in front of it, which just means that from the source, the source is big like this, you're just throwing away all that light.
Yeah.
So in either case, you're throwing away tons of light. And using distance or geometry to filter out everything except a small amount that is spatially aligned. So it's always power inefficient to take that approach. But it's always possible in principle. Okay, now what if I take this incandescent bulb, I'm far away, and I pass it through a 1 nanometer bandwidth or a 0.1 nanometer bandwidth bandpass filter. Then what? What's the degree of temporal coherence? High, because now I have a narrow bandwidth, and I'm still far away, so I have a high degree of spatial coherence. So how did we get this high degree of temporal coherence? Which means we threw away most of the light. Yeah, again, we can always give up efficiency to get coherence if we're starting out with a source that is just by its nature incoherent. Which is really the beauty of a laser, is that you can generate almost all of the light in such a way that you have a high degree of spatial coherence, you're not throwing anything away, and you have a high degree of temporal coherence. That's why the laser was such a breakthrough invention. It's because you get both degrees of coherence with very high efficiency. No other way to do it before. Okay, so now let's do one or two other things. Okay, so these two things and sort of the mental picture that goes with them, that's what you need to know. If you know that, I mean, you're golden for just about everything having to do with coherence. And you don't have to go back and calculate the complex degree of coherence and any of that other stuff. It'll work out. Now, one thing that will be annoying for you is that the notation I just developed is different than the notation of the book. Yeah, lovely. So let me just show you what corresponds to what. Okay, so the mutual coherence in the book, so this is a lecture, and then it's a book. Okay, in the book they call that capital G of R1, R2, and tau. And then the complex degree of coherence, they call that little g of R1, R2 of tau, and tau. And then the temporal coherence, they call that little g of tau. And the spatial coherence, they call that little g of R1, R2. So basically they use big and little g and then play with which arguments are there to clue you in as to what they mean. But at any rate, that's the correspondence. Okay. So, any questions? All right, now really the fun begins. Because now that we understand this stuff, we can use it. And there are fantastic applications of this. So we've got 5 minutes. I could show you one application. Someone want to turn on that projector? And you want to get it all queued up with the screen?
This one's fine.
You already got that.
Yeah. Let's see, can I undo that not?
See how well, oh gosh.
Great, thank you.
Like that. There we go.
That's probably good enough. I understand why this is like the only room that doesn't have an actual projector and screen,
Yeah.
like, installed.
Yeah. It's. Where is that? Yeah. Oh, my goodness. Are you kidding me? Seriously? Okay. Okay, so I'll show you a case where we actually used what we just developed in one of the papers that I published. This is 2006. So we're doing interferometric fiber optic gyroscopes. And for that, you want, at least in a particular embodiment for the gyroscope, you want incoherent light. And yet, what do we have to start with? And it needed to be a fiber-based and waveguide-based design, because this was intended to go into general aircraft for a be able to keep track of where you were, so an inertial guidance system, inertial measurement system. And so because it was going to be a fiber and waveguide system, you need to be able to efficiently couple light from your source into the fibers and waveguides. And if you have just some normal incoherent source, you cannot do that. So we need to start off with a source we could fiber couple efficiently. A laser is a bad choice if we're trying to have incoherent light. So then that means you probably want an LED. And you want a lot of power out of the LED, and you want as big a bandwidth as you can get. So you want a superluminescent LED, so an SLED, superluminescent diode. And so that's what is used here in the configuration where we have the source, goes through a coupler, goes onto a chip that has a polarizer, a splitter, some phase modulators, and then into a fiber coil. In this case, this is a polarization maintaining fiber coil. So you have counter-propagating beams. You want to bring them back together. And you want them to be, the two counter-propagating beams, you want them to be incoherent. Because you're going to look at interference only for one orientation of propagation and not for the other. You don't want any interference between the two orientations. So, long story short, we needed a way of taking that light and making it incoherent. And so, incoherent between the two polarization states. And so what we did was, we said, hey, let's start off with 45-degree linearly polarized light, go through a polarizing beam splitter. So the in-plane polarization is here, the out-of-plane is here, and then bring them back together. And we want depolarized light and incoherent light at that point. And so what we found is that to get depolarized light, we need to make the in-plane and the out-of-plane light incoherent with respect to each other. And so how does one do that? Well, the only thing we can play with here is path lengths. That's it. We can make the TM light have a larger path than the TE light. Okay, we won't go through why it all works and how we implemented it, blah, blah, blah. Instead, this is where we'll go. So we measured the power spectrum of the SLED. So this is power in dB, dBm, as a function of wavelength. And you can see, yeah, that is really broad. And it's got some ripples and things on it. Fine, that's normal. but it's really broad. So once we made the measurement of the spectrum, and had the power spectrum, we could Fourier transform it and get the coherence, meaning the temporal coherence. And this is the temporal coherence as a function of tau measured in picoseconds. And you notice that here, this sort of noise floor is around 30 dB, but that's not incoherent enough for us. So we wanted to go down in one of these little dips, and that dip looked promising, and that happens at a tau of 1.44 picoseconds. So what we did was we designed our setup here so that the propagation time going around here versus here was 1.44 picoseconds different. And voila. Now we have maximized the incoherence between those two polarization states, which is what we need to get depolarized light. Worked awesome.
Really?
Yeah. Yeah. Worked great. And all it really takes is an understanding of this this coherent stuff. Yeah, Mark?
And why is it that you want to depolarize light?
It's how this thing works. So I showed you up above here. This uses a polarization maintaining fiber, and PM fiber is expensive relative to just normal single mode fiber. And so because this was intended to be a mass market thing in the end, the FAA was sponsoring the work, we needed to reduce the cost as much as possible. And so if you're going to have a couple kilometers of fiber, PM fiber is going to be really costly, SM fiber not nearly so costly. So to get away with doing the SM fiber, we needed depolarizers in order to make the system work. And so basically what I just showed you is how we made the depolarizers. Yeah, sure.
And to find power spectral density by taking Fourier transform of the correlation, in the random process stuff we said that the process should be WSS. So I wonder that what condition it brings into this subject.
So I didn't go through all the math of how to get the power spectral density. It turns out it's complicated. And so I had it prepared so we could have gone through it. But in the end I decided, this probably isn't going to be valuable for you to get into all the details, but it's easy to get lost in it. Instead, what I did is I backed up and I went with, okay, just conceptually, what is the power spectral density?
So in this case, we don't have any condition for that. We can use it.
Pretty much, yeah.
All right.
Okay, well, we're out of time, we're over time, so let's call it there.